Welcome everyone. Today we are going to solve the merge to sorted list problem from LeetCode. Well, this problem is a great opportunity to practice your programming skills. We will walk through an efficient and elegant solution that optimizes both time and space complexity. By understanding the logic and implementation behind the solution, you will not only solve this problem, but also gain valuable insights into linked lists, comparison operations, conditional statements, and more. So without further ado, let's dive in. Well, first, let's explore the intuition behind the solution. The problem presents us with two sorted linked lists, list 1 and list 2, and our goal is to merge them into a single sorted linked list. And to achieve this, we will take advantage of the fact that both input lists are already sorted. This property allows us to devise an efficient approach that avoids comparing every node with every other node. The key idea behind the solution is to iteratively compare the values of the current nodes in list 1 and list 2, and selecting the smaller value at each step. By doing so, we can construct a new linked list that merges the two lists while maintaining the sorted order. To begin, we create a dummy node that serves as the head of our merged list. We also initialize a current variable to keep track of the current node in the merged list. Next, we enter a while loop that continues until both list 1 and list 2 have remaining nodes. Inside the loop, we compare the values of the current nodes in list 1 and list 2. If the value of the current node in list 1 is less than or equal to the value of the current node in list 2, we know that the current node in list 1 should come before the current node in list 2 in the merged list. In this case, we append the node from list 1 to the merged list, move the list 1 pointer to the next node, and advance the current pointer in the merged list. Conversely, if the value of the current node in list 2 is smaller, we append the node from list 2 to the merged list and move the list 2 pointer to the next node and advance the current pointer. And by continuously selecting the smaller value between the current nodes, we effectively merge the two lists into a single sorted list. The while loop ensures that we iterate through both lists until one of them becomes empty. And once one of the lists is empty, we know that the remaining nodes in the other list are already sorted. To complete the merging process, we simply append the remaining nodes to the merged list by connecting the current next pointer to the non-empty list. Finally, we return the head of the merged list by skipping the dummy node. By leveraging the fact that the input lists are already sorted, we can avoid unnecessary comparisons and efficiently merge the two lists in linear time complexity. Now, armed with this knowledge, let's proceed to analyze the time and space complexities of the solution. Understanding these complexities will give us insights into the efficiency of our algorithm. First, let's consider the time complexity. In our solution, we iterate through both input lists simultaneously, comparing the values of their nodes and constructing the merged list. This iteration takes place within a while loop. The time complexity of our solution is big O of m plus m, where m is the length of list 1 and m is the length of list 2. And why is this case? Well, in the worst case scenario, we need to compare every node from both list 1 and list 2. Since we iterate through each list only once, the time complexity is directly proportional to the combined length of the two input lists. And in terms of space complexity, our solution is quite efficient. We only use a constant amount of extra space, regardless of the input size. We create a dummy node and a current variable to keep track of the merged list. However, these extra variables do not depend on the size of the input list. They occupy a fixed amount of memory throughout the execution of the algorithm. So the space complexity of our solution is big O of 1, also known as constant space complexity. It means that the space used by our algorithm does not grow with the size of the input list. It's important to note that the space complexity does not include the space required to store the output merged list itself. The space complexity only accounts for the extra space used by the algorithm, and in this case, it remains constant. Overall, our solution efficiently merges two sorted linked lists in linear time complexity and with constant space complexity. This makes the highly optimized solution capable of handling large inputs without incurring significant memory overhead. Understanding the time and space complexities of our algorithm is crucial for evaluating its efficiency and scalability. It allows us to assess how the solution performs as the size of the input lists increases. And there you have it. We have successfully tackled the merge to sorted list problem from LeetCode. Congratulations! Remember, practice makes perfect. I encourage you to continue honing your skills by exploring similar problems on LeetCode. The more you practice, the more confident and proficient you will become in solving algorithmic challenges. I hope you found this tutorial helpful and informative. If you have any questions or need further clarification, please don't hesitate to ask in the comments section. Your feedback and engagement are greatly appreciated. And if you enjoyed this tutorial, be sure to give it a thumbs up and subscribe to the channel for more coding tutorials, tips, and tricks. Happy coding, and thanks for watching. Goodbye.